In this video, I'm going to talk about a couple of the natural phenomena that we see with light and colors in particular. So things like, why is the sky blue and why are sunsets red? So to start with, something we should point out is Roy G. Biv. These are the 7 colors of the rainbow. In truth, there's an infinite amount of colors in here. But for now, the key thing to note is that the wavelength gets shorter. Wavelength gets shorter. There we go. As you go from R to V. The next thing we need to note is that our atmosphere is nitrogen-based. You may think, well, I breathe oxygen. Yeah, you do. But only about 21% of what you breathe in is oxygen. About 78% of it is nitrogen. That's fine. Nitrogen's harmless to you. It won't do anything. It's been here the whole time. It's not something new. In this diagram on blue, we have the outline of the atmosphere, and green's the planet, and here's a person standing on the planet. Now, this is obviously not drawn to scale. The atmosphere is nowhere near this thick, but I just drew it that way so that way I can kind of draw the point that I want to make. One of the things we have to point out is that our nitrogen-based atmosphere favors scattering short wavelengths of light, like your blues, indigos, and violets. Will it scatter red? Absolutely. So let's imagine some red lights coming in from the sun, and it strikes our atmosphere. Does some of it get scattered? Yeah, it does. But we're only talking a little bit. The overwhelming majority of the red light is going to go right through the atmosphere. What about green? Green's a longer wavelength than red, so will it scatter? Absolutely. It'll scatter probably a little bit more than, say, the red would. But the bulk of it is still going to get through the atmosphere and come down to you. This is in part why the sun appears very yellow to us on Earth, because if you mix red and green light, you get yellow. Astronauts do notoriously say that when they go into space and they actually see the sun from the point of view of outer space, they point out how very white the sun looks. And that's because our nitrogen-based atmosphere does a fantastic job of taking a lot of the blue light and scattering it. So a very heavy amount of blue light gets scattered all throughout our sky. Does some break through? Absolutely. Some of it breaks through. But a lot of it gets scattered. So then what happens after it gets scattered? So it's broken through the atmosphere and it's gone here. So if we follow this wave, hit the atmosphere here, scattered off in this direction, hits this portion of the sky. Well, what does it do after it hits that portion of the sky? It reflects, and it comes back down to you. This wave started here, scattered, came out here, and it reflects and comes back to you. So from your point of view, wherever you look in the sky, you're looking at blue light that broke into the atmosphere at one place, shot off to another place, bounced off the atmosphere, and then reflected to you. That's why the sky tends to appear blue. Some people have pointed out, well, violet is a shorter wavelength than blue, so why isn't the sky violet? That's a good question. And in truth, you could argue that, well, it kind of is reflecting more violet light than blue light. But as a human being, we have 3 cones in our eyes, red, blue, green, which means you are far more sensitive to blue light than you are to violet light. Now, do the reds and greens get scattered in other parts of the sky? Absolutely. And that's why when you look at the sky, you'll notice that the sky isn't always a uniform, perfect, one blue color. It changes based on where it's at, and it gets a lot more complicated with these angles. Say, for example, at what angle is the sunlight striking our atmosphere? That will play an impact. That leads to the second thing that I wanted to talk about today, and that is, why does the sunset appear red? So I want you to view this version of the planet as here's the North Pole, and our planet spins this way. So our individual here is at sunset, okay? Now what's going to happen is as the sunlight comes from the sun and it strikes the atmosphere, this angle is too sharp and it's going to bounce off. Green light does the same thing. Angle's too sharp, it bounces off. The red light, which is the longest wavelength, breaks through the atmosphere. Breaks through the atmosphere far more easily than than the green and the blue. The red light has the longest wavelength, which means it has the least amount of interference from our nitrogen-based atmosphere. Eventually, what's going to happen, if you remember what as I talked about, the green and the red mixed together make yellow. That's why the sun appears very yellow. You go into outer space, you don't have the scattering of the blues anymore, so the sun appears very white. Well, at sunset, a lot of the green gets scattered away. The majority, if not all the blue, gets scattered away. The red, the longest wavelength, is what breaks through, which is why the sun appears red at sunset. And that highlights another interesting point about our moon, which is back here. During a lunar eclipse, the moon, prior to being eclipsed, is actually going to appear red. And that's because the red light at these sharp angles, like you saw here, as well as here, are going to go through the atmosphere, make it onto the other side of the planet, and then bend towards the moon. The Earth's atmosphere is acting like a lens and focusing the red light onto the moon. Now, why does this happen on every full moon? Because the moon moves up and down sinusoidally in its orbit, and it's not always perfectly in a level plane with the sun and the Earth. Therefore, it's not always directly behind the Earth, which is why we only have a lunar eclipse every couple of months, as opposed to every single month when there's a full moon.